In this video, you will learn R and R squared visually and clearly. We often use the correlation coefficient R to see how two variables relate. It tells us the strength and direction, ranging from -1, perfect negative, to +1, perfect positive correlations. This figure indicates no correlation. The value close to 0 from positive side indicates weak positive correlation, and a value close to 0 from negative side shows a weak negative correlation. The value close to -1 is strong negative. The value close to 1 indicates a strong positive correlation. But here is another value that is perhaps more powerful for understanding your data. R squared, also known as the coefficient of determination. Now, R squared can be calculated in two ways. First, it can be calculated just by squaring of correlation coefficient R, and second, it can be calculated through sum of squared errors. Let's start with the first method. The correlation coefficient R is the covariance of x and y divided by the products of a standard deviation of x and a standard deviation of y. The easiest way to find R squared is to simply squaring the correlation coefficient. It is a simple calculation, but it shifts the meaning from how do these move together to how much of this change is actually caused by the model. While R shows the direction and strength of correlation between two variables, ranging from -1 to +1, R squared shows explanation. Specifically, it tells us the percentage of variation in the dependent variable y that can be explained by our independent variable x. It always ranges from 0 to 1. Method 2, the visual logic, sum of squares. To truly understand R squared, we need to look at how much error our model eliminates. Let's look at a dataset of income versus years of experience. Imagine we have no model at all. Our best guesses for everyone's income would simply be the average or mean. If we plot that mean as a horizontal line, we can measure how well it fits the data by calculating the distance between each data point and that line. Because distances above and below the line cancel each other out, we square those differences before adding them up. This is the total sum of a square, or TSS. It represents the total variation or error in our data before we add any extra information. In our example, the TSS is 5,450. But here is the question. Is the mean really the best way to predict income if we already know someone's years of experience? Probably not. Now let's draw a regression line. This line follows the linear trend of the data. To see how much better this line fits, we calculate the sum of squares again. But this time, we measure the distances from the data points to our new blue regression line. This is the residual sum of squares. In our example, the RSS drops significantly to just 456. Visually, the blue line clearly fits the data better than the mean. But by how much? This is where R squared comes in. R squared is the difference between the variation in the mean and the variation in the regression line, divided by the variation in the mean. Or mathematically this. Since the sample size n cancel out each other, we use our sum of squares. Because the error around the regression line is never less than 0 and is smaller than the error around the mean, this formula gives us a value between 0 and 1, which we can express as a percentage. In our case, using least squares regression reduced our sum of squares, or in other words, reduced prediction error from 5,450 to 456. The reduced prediction error is 4,994. As a percentage of the original error, the result is 0.91. This means there is 91% less variation around our regression line than variation around the mean, Or in other words, 91% of the variation in income can be explained by the years of experience. Let's compare different models. What if the data is messy and the correlation is weak? Images comparing two scatter plots, one with points tied to the line, high R squared, and one with points widely scattered, low R squared. Scenario A. TSS is 5000 and RSS is 4500. R squared is 0.1, meaning that variation around the regression line is 10% less than variation around the mean. Or in other words, only 10% of the variation in income is explained by the years of experience. The model isn't very helpful for predicting income. Scenario B, our first example. R squared is equal to 0.91, meaning 91% of the variation in income is explained by the years of experience. This is a very strong, reliable model. Don't forget to subscribe for more tutorials on statistics and data analysis.